looking at section 2.3, which is about characterization of invertible matrices. We start with the theorem, which actually culminates our knowledge or our information that we have collected in these three sections, 2.1, 2.2, and now 2.3. And it combines all the statements of the theorems or results that we have seen into like one big theorem. So we are not, of course, going to prove in any of these, but we have to kind of remember at least some or connection of some. Because if one of them is zero not true, then all are not true. And if one of them is true, then all of them are true. So theorem 8 says, let A be an n by n square matrix, then the following statements are all true or all false. First is A is an invertible matrix. 2 is A is row equivalent to the n by n identity matrix. Number 3, A has n pivot positions. 4, the equation Ax is equal to 0 has only the trivial solution. 5, the columns of A are linearly of A form a linearly independent set. 6, the linear transformation which takes x to Ax, the matrix A times x, is 1 to 1. The equation Ax is equal to B has at least one solution for each B in Rn. The columns of A span Rn. 9. The linear transformation that maps x to Ax maps Rn onto Rn. So this is for onto. Number 10, there is an n by n matrix C such that the CA is equal to I. This is the identity. This will be the inverse matrix. There is an n by n matrix D such that AD is equal to I. Now notice here, the inverse which x from the left could be different from the inverse with x from the right over here. And number 12, A transpose is an invertible matrix. So if A is invertible, A transpose is also invertible. So all these results you can use in finding out the answer to your question. And so let's see how it works. But note here, if A and B are square matrices such that A times B is equal to I, then A and B are both invertible with A inverse equal to B and B inverse equal to A. So they are inverses of each other. Now we talk about invertible linear transformations. So we say a linear transformation T from Rn to Rn. So now here, notice here that this is the same. In previous cases in section 1.9, we had different. We had Rm to Rn. But in this case, we are talking about square matrices because we want to involve the invertible matrices here. So a linear transformation from Rn to Rn is said to be invertible if there exists a function s from Rn to Rn, again such that s of t of x is equal to x and t of s of x is equal to x for all x in Rn. Now, if you recall, this is exactly following or copying the definition of a function and its inverse. So if you have a function f and if their function can be inverted, if the inverse can be found, that f of f inverse of x gives us back x, and similarly f inverse of f of x give us back x. So similar thing here. If such an S exists, then it is unique and must be a linear transformation. So if T is a linear transformation, then the inverse must be a linear transformation. And we call this S the inverse of T and write it as T inverse. So this statement of here the equation could have been T inverse of T of x equals x. So see the similarity with the functions. So the second one becomes T of T inverse of x is equal to x. The next theorem, let T from Rn to Rn be a linear transformation and A be a standard matrix for T. This y is extra here. That is that we can write T of x as A times x. Then T is invertible if and only if A is invertible. In this case, the linear transformation S given by S of x is equal to A inverse of x is unique and satisfies equations 1 and 2 above. So how do we find the S? T is defined from T is defined as Ax. S, the inverse will be defined as A inverse x. Okay, so let's look at example. There are not many here, just a couple of examples. So determine whether the matrix is invertible or not. Now, if you are given a matrix, you have to find out whether it is its inverse exists or the matrix is invertible or not. We can write down the augmented matrix with the identity matrix and do our whole procedure, the row operations, and figure out whether the inverse exists or not. But in some cases, you can actually, by looking at the matrix and remembering the three conditions of the linear independence, you can actually talk about the inverse existence of inverse. So the first, because going back up here, A is an invertible matrix. So A will be invertible matrix if A is rho equivalent to n by n identity matrix. So this is what we have in the situation when we have we find the inverse. Then the third point is, or third statement is, A has n pivot position. Well, in our case, we cannot see. We see that it doesn't have 3 pivot positions there, but maybe when we work, if you can see, there will be 3 pivot positions, then you can say it is invertible. Okay, what else can we see? The columns of A are linearly independent sets. So if A will be invertible if the columns are linearly independent set, and if we can show that the columns are not linearly independent, which we can state from here because there is one column of 0 vectors, we can say not invertible because of the 0 vector. Or 0 column. So they are not, columns are not linearly independent. So the matrix is not inverted. Now looking at this next matrix, notice that it is in echelon form. And you can see, and there are pivot positions in each row. Okay. So if there are pivot positions in each row, then A is invertible. Therefore, this matrix is invertible. That's it. Okay, next one. So now we have dealt with some transformations before, but now so it's asking us to check whether T is invertible or not, and if it is, then we have to find a formula for the inverse transformation. So what we do, basically, we first try to find our A. So as I have shown you, if you write this transformation as 6x1 minus 8x2, and then minus 5x1 plus 7x2. So if you write it like this, you can easily see the A matrix A. So it will be 6, -8, -5, 7, and then x1, x2. So the right hand side can be seen like that. So A is, so we can say this is equal to AX, where A is 6, -8, -5, 7. Okay, now we want to find the inverse of this matrix. If the inverse exists, then it means that T is invertible, and then we have to find the formula for T inverse. How do we check whether inverse exists in a 2 by 2 matrix? We find the determinant. So determinant of A, 6 into 7 minus -8 into -5. So I get 6 times 7 is 42 minus, so this minus negative, there are 3 negative signs, so we get a negative, minus 40, we get 2. So that A inverse equals 1 over 2, 1 over the determinant times the matrix. So what we do with the matrix, we exchange the A and the D positions, means this position and this position. So this one and that. We exchange them, and then the other two we change their sign. So 7 comes here, 6 goes here, this becomes 8, and this becomes 5. That is your A inverse. Now we have to go one step further, and if there is a scalar in front, we have to multiply over each entry of the matrix by that scalar. So it becomes 7 over 2, 4, 5 halves, and then 3. This is the inverse, A inverse matrix. So what does this imply? This implies T is invertible. And what is T inverse? T inverse of X, as stated by the theorem 9 above, it will be A inverse X. So will be equal to 7 halves, 4, 5 halves, and 3 times x1, x2. So now multiply it out. So notice that we are going backwards now. So 7 over 2x1 plus 4x2, and the second is 5 over 2x1 plus 3x. So therefore the formula for T inverse of x as would be given 7 over 2x1 plus 4x2, comma 5 over 2x1 plus 3x2, and that's it. That is our formula for the inverse transform. So that's it for 2.3.